Hi there, this is MG5004 and DE5418, topic 7 class 1. A matrix is a set of numbers, whether with real numbers or complex numbers, that are just arranged in rows and columns. Like that, if you can imagine that they were numbers. And we talk about this having an order. We say that this particular one has order m by n, and it's m rows by n columns. And in this one, this has 1, 2, 3 rows and 1, 2, 3, 4, 5 columns. So the order of that one is 3 by 5. If we want to talk about a single unit in here, we would talk about it as A, I, J, if the matrix's name was A. And what we've got here is we've got the suffix, we're talking about a double suffix notation here, but it's also a subscript, so it's a subscript suffix notation. And what we're talking about is that we're talking about here the element that's in the ith row and the jth column. So the one that I've marked there, if we're calling this A, then this would be element in row 3 and column 1. So that's that element there. Now a vector is just a list, and a matrix is lots of lists. So it's not a particularly obscure thing, it's just a lot of lists, but it has some rules, of course. If we have the same number of elements in the rows and the columns, then the matrix is square, and then we'd call it a square matrix, and we talk about its order being n. And if we were to take one of the columns, we would actually say that it was a column vector, or we took one of the rows, we'd call it a row vector. And that's what I said on the previous slide, that a matrix is made up of lots of vectors. That's just reminding me that I'm actually making your videos. Okay, just a bit of nomenclature here. We tend to use the uppercase for matrices, so we'd use a capital A for the matrix, and we would use lowercase for talking about vectors. And a vector is normally taken to be a column vector unless you're told otherwise. So if we're talking about a vector, in general it's a column vector. We talk about the trace of a matrix being the sum of the leading diagonal, the elements in the leading diagonal. It's got to be a square one, otherwise it won't have a leading diagonal. And we talk about a diagonal matrix where all except that leading, it's the leading diagonal there, where every other one is 0. We talk about the identity matrix or the unit matrix. So the identity matrix. And we'd use I for that. And sometimes we just use a bit of notation, that the Kronecker delta symbol, we'd say that. And what we mean is that the element is equal to 1 if I equals j, and 0 if I doesn't equal j. So if we're talking about element 1, 1, then the it would be, the element would be 1, whereas if we're talking about some other element, it would be 0. So if we talk about 2, 2, it would be 1, and if we're talking about 3, 3, it would be 1 as well. Sometimes we need I to be bigger than 3 by 3, in which case we'd talk about it as being I4, and we'd be 4 by 4, so it would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, like that. We also talk about the null matrix. Now this is usually in a textbook, it's usually in bold, so it would be O, and it would be all the zeros, and it would be big enough. It would be as big as you needed it, like that. When we come to look at inverses and things, we need to know about the transpose of a matrix, and sometimes you see them written as A and a T like that, and all it does is you're taking the first row and making it become the first column, and the second row becomes the second column, etc. So for the one that's shown on the slide, 467925, the transpose will become, so the first column will become the first row, 472, and then the second column will become the second row, like that. And if we look at A is 3 rows by 2 columns, then A transpose must be 2 rows by 3 columns. We talk about a symmetric matrix where the transpose is equal to the original, and so you get this relationship here where the element ij is equal to the element ji, and we also have what we call a skew symmetric matrix where the transpose is equal to the negative of matrix A. That means the element aij is equal to the opposite of the element ji. Let's have a look at some examples of that. Let's have a look at 1, 2, 5, 2, 8, 9, 5, 9, 4. And we can see that this one is symmetric. The numbers are symmetrically placed across that diagonal. Here's an example of a skew symmetric matrix. 0, 2, 5, negative 2, 0, 9, negative 5, negative 9, 0. So you can see there that there are pairs of elements, the negative 9 and the 9. One's negative and one's positive, and the same for the 5. One's negative and one's positive, and for the negative 2 and positive 2. So there's the sort of axis of symmetry, if you like, and they're the same number but different signs. Pretty obviously, two matrices are equal if their corresponding elements are equal, but if we're going to add them or subtract them, then they've got to be of the same order. And this is because when we find the sum, we subtract, we add corresponding elements. So if we've got A is equal to 4, 6, 5, 7, 3, 1, 9, 4, and B is equal to 2, 8, 3, negative 1, 5, 2, negative 4, 6, then A plus B, we're going to add corresponding elements. Oops, that's not 86, that's 86, and 8, 3, 5, 10. And if we were going to find A minus B, it would be 2, negative 2, 2, 8, negative 2, negative 1, 13, and 2. So we're subtracting corresponding elements. Quite a few of the slides as we go through will just be lists of rules, but you do need to know them. that the transpose of a sum is equal to the sum of the transposes. The transpose of a transpose is what you started with. The sum of the transpose and the original transposed is going to give you ultimately the original plus the transpose, and you can jiggle around with making A equal to half the matrix and plus its transpose plus half the matrix, half times the matrix minus its transpose, and that's just an algebraic thing if you expand your brackets. I've mentioned these special matrices already, the unit matrix or the identity matrix, and as you would imagine, this is the equivalent in multiplication to 1, to multiplying by 1. So A times the identity is equal to A, which is equal to the identity times A, which is also equal to A. And then I mentioned before the null matrix, which we call O. And if A times B is equal to 0, then A is not necessarily 0 and B is not necessarily 0. We will do multiplication shortly, but the example there in actual fact gives us an answer of 0, 0, and clearly neither of them is 0, neither A nor B is 0. And when we do multiplication, we'll look and we'll see that BA is actually not possible in this case. More rules about addition. Matrix addition is commutative and associative, and the distributive law works with it. So for example, if we've got A is equal to 4, 3, 2, 7, 6, 1, and B is equal to 5, 4, 9, 0, 2, 8, then 5 times A plus B, and we can work out what A plus B is. A plus B will be 9, 7, 11, 7, 8, and 9. And if we're going to multiply that by 5, then our rule would say that that's equal to 5A plus 5B, and we can show that that's equal to 45, 35, 55, 35, 40, and 45. And if we were to work out what 5 times A was and 5 times B was, it would be the same. We need to look at matrix multiplication, and there's only sometimes that you can do it. You can only do it when the number of columns in the first is equal to the number of rows in the second. And the easy way to look at it is if these two numbers here are the same, then you can perform the multiplication. Otherwise, you can't. And it is a complicated process, and it is one where you're likely to make mistakes, but you're only likely to be making arithmetic mistakes, not actual mistakes as they are. Let's have a look at if A equals 1, 5, 2, 7, 3, 4, and B is equal to 8, 4, 3, 1, 2, 5, 8, 6. Now the first check would be to see if we can do it, and A is 3 rows by 2 columns, and B is 2 rows by 4 columns, and yes, this number is the same as that number, so yes, we can do that multiplication. So all it is, we just follow the formula, and AB is going to be equal to, now I hope I have enough room in here, multiplying 1 by 8 plus 2 by 5, so that's 8 plus 10, and then it would be 1 times 4 plus 5 by 5, so it would be 4 plus 25, and the next one over would be 3 times 1 plus 5 times 8. And the last element in the top line would be 1 by 1 plus 5 by 6, so 1 plus 30. Now I'm not going to go through all of them. I will just fill them in. It'll be that was a 56. 2 plus 42. 24 plus 8, 12 plus 20, 9 plus 32, and 3 plus 24. And adding them all up, we get 18, 24, 43, 31, 30, 43, 62, 44, 32, 32, 41, 27. And as predicted, that is a 3 by 4, because there's our answer there, 3 by 4. More rules. Multiplication is not commutative. Associative is commutative under multiplication. Multiplying by a number, a scalar, that all works. Expanding the brackets, that all works. And I and IM and IN are just unit matrices, and we need them to be units in orders M and N respectively. We're going to use the determinants of a matrix or matrices when we come to solve equations, to solve systems of equations using matrices. That's one of the big things that we use matrices for. So we need to find the determinant. The determinant is a single number, and it's got a rule for working it out. And you can do it anywhere along the matrix. Here's the rule for it. Here the determinant is A11 times A22 minus A12 times A21. So if we've got a matrix 5, 2, 1, 0, 6, 3, 8, 4, 7, then no matter which row we do, then we're going to get the same. So let's do it along maybe the first row. So it would be using down here, it would be A11, so it would be 5 times, now we need to work out 42, which is 42 is 6 times 7 minus 3 times 4 minus 2, which is the next element along, times 0 times 7 minus 8 times 3 plus, and the third element is 1, times, where are we at, 0 times 4 minus 6 times 8. And if we do all of that, our determinant, if this is A, is 150. So the determinant of that is 150. We could also find that the determinant, not just of A, but the determinant of the transpose was also 150. and all you need to do is find the transpose by rearranging the rows and the columns and then doing a similar calculation. We talk about the minor of an element, and previously on the previous slide we found the determinant of this, and that is what we call the minor. So the minor of A11 is the determinant of the other 4 units, and we need to use the place signs. As you saw, some of it was plus and some of it was times, and the place signs come from the place sign matrix plus, negative, plus, etc. Let's just have a look at an example. Say we've got A equals 2, 3, 5, 4, 1, 6, 1, 4, 0. Now the determinant is going to be 2 times the determinant of 1, 6, 4, 0 minus 3 times the determinant of 4, 6, 1, 0 plus 5 times the determinant of 4, 1, 1, 4. Sorry, I'm just trying really hard to squeeze it in there at the edge. So then if we work out the determinants of the little bits, it's 2 times 0 minus 24 minus 3 times 4 zeros minus 6 plus 5 times 4 fours is 16 minus 1, and if you do the arithmetic it's 45. Now it doesn't matter if we use the second row. I've used the first row. I found the determinant by expanding the first row there, but it doesn't matter if we do it on the second row either. If we did it along the second row, it would be negative 4 times 3 times 0 minus 5 times 4. Now look, on the second row it has to go minus plus minus, so it would be plus 1 times 2 times 0 minus 5 times 1, and then the last place sign would be minus 6 times 2 times 4 minus 1 times 3. And we should find the numbers the same. We should find that that's 80 minus 5 minus 6, which looks to me like 45. Lots and lots and lots and lots and lots of rules there. Most of them are pretty straightforward. Read through them, have a working understanding of these rules and the ones on the next page. And more rules. I will do examples of both these and the previous slide in class. Now we talk about the adjoint, or the adjugate, I prefer to say adjoint matrix, and it's the transpose of the matrix of the cofactors. So we could write that as A dj, A equals the transpose of the matrix of the cofactors. And a few facts there. It tells us A adjoint A is equal to the determinant of A times the identity, and the adjoint of A is equal to the determinant to the power of n minus 1, and the adjoint of AB is equal to the adjoint of B times the adjoint of A. So really this is the important thing here. This is the crux of the matter here. It's a way of finding the inverse of a matrix, and we'll do an example of that in class 2. By definition, a square matrix is called non-singular if the determinant doesn't equal 0, and singular if the determinant does equal 0. Let's have a look at the example here. The determinant is negative 2 times 1 minus negative 2 times 3, so it's 4. So this is non-singular. This is a non-singular matrix. It's easy to read that first line if we think about it, that the inverse of A is A to the negative 1, such that A times the inverse, as you would expect, equals I. And in this case only, the multiplication is commutative. We already know from the previous slide that A times the adjoint is the determinant times the inverse. So flipping this around a bit, transposing this, we get that the inverse is the adjoint over the determinant. So now what we've got down at the foot of the page is if A and B are both square matrices and AB is equal to the identity, then BA is equal to the identity as well. So previously, let's look at 2, 3, 5, 4, and 6, 1, 4, 0, I'll call that A, and the transpose of the cofactors we've already worked out. This one is the adjoint of A. So our inverse is 1 over... Now this is why we needed the determinant not to be equal to 0, because if the determinant is 0, then we can't find the inverse. So the inverse is 1 over the determinant times the transpose of the cofactors, and we've already found that the determinant is 45, so it's 1 over 45 times negative 24, 20, 13, 6, negative 5, 8, 15, negative 5, and negative 10. And if we do all of that, then we're done. What we can prove is that A times the inverse of itself will be equal to 1 over 45 times 45, 0, 0, 0, 45, and 0. Oops, so that should be 45. No, start again. What I'm trying to say is that that should be 1 over 45 times 45, 0, 0, 0, 45, 0, and 0, 0, 45, which obviously, if you work it out, is equal to the unit matrix. So to summarize that, to find the inverse of a matrix, find its determinant, find the matrix of its cofactors, transpose that, and then divide the adjoint by the determinant, and that is the inverse of A. And of course there's rules. The inverse of the inverse is the original. The inverse of AB is the inverse of B times the inverse of A, provided you can invert both of them. The transpose of the inverse is the inverse of the transpose, and the determinant of the inverse is the inverse of the determinant. We will come back to actually doing this later, but the way we do it is we rewrite the equations in the form AX. So for this one, we would write it 1, 2, 1, 3, negative 4, negative 2, 5, 3, 5, and that would be multiplied by x1, x2, and x3, and that would be equal to 4, 2, -1. So A times X is equal to B, and then X1, X2 and X3 will be equal to the inverse of A times B. It's the nearest we can come to matrix division. And if this is B, if that's 0, then we talk about the equations being homogeneous, and if B is not equal to 0, then the equations are non-homogeneous or inhomogeneous. And we say that there's a non-trivial solution if the determinant is equal to 0. This is one way of using a rule called Cramer's rule to work out what X and Y are in the system of equations given there, and it requires you finding the determinants of various little matrices. Dx is the determinant of B1, B2, A12, A22, and so on. And there's another way that I'll show you on the next slide. All we've done here is I've rearranged the equations, so instead of having B1 and B2 on the right, I have put them on the left. Now, B1 and B2 might be negative numbers, it doesn't matter, but it gives us a slightly different way of working out X and Y. I will do question 1 now on a separate slide, and I'll do question 2 in class. So using Cramer's rule, we know that X over the determinant of -4, -12, 5, -6.5 equals -y over the determinant of 3, -12, 7, -6.5. And both of those equals 1 over the determinant of 3, -4, 7, 5. So just some number crunching now. So X over -4 times -6.5 minus -12 times 5 equals -y over 3 times -6.5 minus -12 times 7 equals 1 over 3 times 5 minus -12 times 7. So then we have that X over 86, after some number crunching, equals -y over 64.5 equals 1 over 43. And then we can do, I don't know, X over 86 equals 1 over 43. So X is equal to 2. And -y over 64.5 equals 1 over 43. So that gives us y equals -1.5. Slightly different version there. It makes no odds. It's just different letters. Doesn't make any difference. Might be useful to write in here that X is equal to the determinant of B1, A12, A13, B2, A22, A23 over B3, A32, A3. Oops, a daisy, that line just appeared. Let's get rid of that line. Over the determinant of A11, A12, A13, A21, A22, A23, A31, A32, A33, and so on. That's using that method there. If we're going to use the slightly different notation, then x would equal k1 b1 c1, k2 b2 c2, k3 b3 c3 over the determinant of a1 b1 c1, a2 b2 c2, a3 b3 c3, etc. For this example, I've worked out all of the little bits. So x is going to be equal to dx over d, which would be 70 over 35, which is 2. Y is equal to dy, the determinant of y over d, which would be negative 105 over 35. And z is equal to dz over d, which equals 175 over 35, which is 5. You can do this by Excel, and I'll show you in class how to do this using Excel. In class, I will also give you a handout of another way to solve this.